Alright, so we are supposed to draw corresponding velocity time graphs for these initial position time graphs. And so let's start with the first one. Remember, we know the equation that average velocity is equal to change in position over change in time. Okay? And as long as it's not average velocity, as long as the velocity isn't changing, not only does this tell us average velocity, but it tells us instantaneous velocity, because the velocity here is the same as the velocity here, as this velocity here is here. Okay? And so we're going to look at this first time interval from 0 to 3 seconds, and we want to know what its velocity is. Well, that's just rise over run, so change in x over change in time, which equals 2 minus 5 over 3 minus 0, which equals negative 3 over 3, which is equal to 1, negative 1 meter per second. So over here on my velocity time graph for the first 3 seconds, I know I have negative 1 meter per second. The next couple seconds, okay, from 3 to 5 seconds, my change in x is 0. If I have no change in position, that means I'm not moving. So my velocity is also 0 during this time interval. And then from 5 seconds up to 7 seconds, I've got a change in position of, 6 minus 2 equals 4 meters, and a change in time of 2 seconds. So this is 2 meters per second. So my velocity's got to jump all the way up to 2 and stay there for the duration of the graph. Okay? So this one's fairly straightforward. We're just graphing slopes. Slope of negative 1, velocity is negative 1. Slope is 0, slope is 0. Slope is positive 2, velocity is positive 2. We got to be a little bit more careful though on this second one, because this one has this curving line, right? And that curve means that the velocity isn't constant. Okay? And so average velocity is the same as instantaneous velocity as long as the velocity is constant, but this is not a constant velocity. So we do know our average velocity, but that might not be what we want. Instead, let's look at what this shape does. It starts slow, so it looks flat. So I'm going to say it starts 0 meters per second. 2 seconds later, it needs to have gotten faster, okay? And it's moving away, so it's got to be somewhere along this axis, right? That dashed line. Well, let's see how far it's gone. It's gone a distance of 2 meters, right? 2 minus 0 is 0. So our change in x equals 2 meters. Our change in time is 2 seconds, which tells me my average velocity is 1 meter per second, but it was only going 1 meter per second for like maybe 1 instant in time. Okay? But I also know from a velocity time graph that area equals displacement, and so I know that the area of a triangle is 1/2 base times height, and I know that the base is the time, and that's 2 seconds. I know that the height is however fast it's going at the end, and I know that this area needs to be 2, right, because our displacement is 2. Well, 1/2 of 2 is 1, and so now I have 1h equals 2, and so I have the height equals 2. So that means 2 seconds later, this object was moving at 2 meters per second, and I can connect that line. Now let's do a quick double check. Is the area of this triangle 1 or 2? Let's see, 1/2 base times height, 1/2 2 times 2. So yeah, the area of this triangle is 2, and that matches the displacement here, 2 meters. Okay, the next 2 seconds, it moves from 2 to 4 meters in 1 second. So now it's moving at this constant rate of 1 meter per second. Okay, right? Change in x is 2, change in time equals 1, so 2 over 1 is 2 meters per second. So that's a straight horizontal line. And then 4 to 6, let's see, that's 2 meters in 4 seconds. So that's 1/2 meter per second. So this has got to drop all the way down to here and hang out down at 1/2 for the remainder of the graph. Okay? So this curved line is a little bit tricky, but remember, A curved line on a position time graph indicates the velocity is changing. A sloped line on a velocity time graph indicates the velocity is changing. So they match. Finally, you guys needed to do this last one on velocity and take that and get position. Now, the only way you can do that is if I tell you a starting point, and I did. I said assume it starts down here at the origin. Alright, so then we've got intervals. So I'm going to look at this interval here from 0 to 3 seconds. From 0 to 3 seconds, the object moved, it looks like at 2 meters per second. So if I find this area, that's 3 times 2, which equals 6 meters. So I know in 3 seconds, I've got to get over to 6 meters. Okay? And it's constant, so that means I have a straight line. Now the other way you could do that is you could say, well, this is the slope. The slope is 2, so that means up 2 over 1, up 2 over 1, up 2 over 1, and we end up in the same spot. Now, for the next second and a half, right, this is my next interval, because when it hits the origin, it crosses, or when it crosses the axis, it reverses direction. That's a change. We need to pay attention to it. So my interval is this 1.5 seconds. What happens? Well, it's still moving away because this is still positive, but it's slowing down. And how far did it go? Well, the area here is 1/2 base times height, which is 2 meters. So I know in the next second and a half, so at 4.5 seconds, it needs to have gone all the way to 8 meters. But it's not a straight line this time because it's slowing down. So it starts steep and curves flat. Okay? And then for the next second and a half, so all the way over here at 6 seconds, okay, what's it do? Well, here my area is 1/2 base, which is 2 seconds, times height, which is -2, right? It went from 0 to -2. This is -2 meters. So it comes back the other direction, but this time it starts slow, starts close to 0, and ends at 2 meters per second. So it starts slow, gets faster. That's a downward curve. And then finally, it stays at -2 meters per second for that last second. So it slopes down like that. Okay? So if we go in reverse, does this graph make sense? We've got a slope of 2. Okay, 6 over 3 is 2. I've got a velocity of 2. I've got a line that says start fast, get slower until it stops, get fast, stop. That works. From stop, move towards the origin, getting faster. From 0, speed up, moving towards the origin, and then move at a constant rate. So yeah, this looks good.